Okay.
This meeting is being recorded.
Wonderful. Okay, so hi everybody. My name is Liam. It's good to see some new faces and some returning faces. So far, we've been going through the mathematics for machine learning textbook, and we are at chapter 8. Up until here, we have been going over the mathematical foundations such as probability theory, linear algebra, and sort of the atomic components of machine learning. And in this the first chapter of section 2, we're actually going to get into where models meet data, or when the rubber hits the road. So very exciting. So yeah, let's begin. So for those who are not familiar, I'm going to go over sort of what was discussed in the chapter. This chapter had a lot of sections that were classified as further reading, so I did a little bit of digging into some of those concepts, and periodically we'll leave it open for some questions and some comments if anyone has any particular experience that they want to add to the situation. It's always welcome. This is a book club, not necessarily me just talking about this stuff, so feel free. But to start off with, the chapter began with kind of defining what a model is, and the authors kind of lumped this into two main categories. One being a model that is a predictor of a particular value, and they called it a predictor. And then a model that is a distribution. So a predictor has a deterministic output. As you can see, it has you have an input, which is a d-dimensional real numbered vector or matrix of some kind, vector. Or a series of vectors, and it outputs like a real number. The example that they gave was actually in that second equation there. Let's see if my mouse is, yes, which is an affine transformation or family of affine transformations with these parameters theta. So the difference being, a predictor outputs a particular value, a distribution outputs a distribution, and some examples of predictor functions are linear regression, support vector machines, decision trees, and neural networks. You can also use a neural network to find a distribution, but you generally train it with a concrete input and output. And if you want to use it to get a distribution, you take you split it apart and you use it as an encoder. But for standard tasks, neural networks are functions. And some examples of probabilistic models are logistic regression, naive Bayes, Gaussian processes, and hidden Markov models. I'm going to go briefly into a little bit more detail on hidden Markov model as an example. I'm not going to do a huge deep dive, but just to give an example. And then hyperparameters, as opposed to parameters. Parameters are learned through training, whereas hyperparameters are set before training to kind of influence model structure and behavior. Some examples being learning rate, batch size, and number of layers. So starting off with empirical risk minimization, this is basically how we deal with the loss function for deterministic or non-probabilistic models. This should kind of be somewhat familiar that we have, the training error and then we have the test error. But in more concrete terms, we have this, what's called empirical risk, which is, the mean or the average of all of the losses between the predictions and the outputs. I've actually seen it be a sum before, not a mean, but in vast majority of cases, it should be a mean of the loss. So that's called the empirical risk, and that's what we want to minimize. This depends on the model, the data X, and the labels. And it also assumes that the data points are independent and identically distributed, which is IID. And that's actually true with maximum likelihood estimation, which I'll get into in a bit too. But really, we don't actually care about this empirical risk. We actually want to try and get a model that predicts the expected risk, which is, the loss of the population, how well it's going to perform on all data. And that ends up being the expected value of the loss. So at that point, the chapter gives a good sort of definition of overfitting, which I really appreciated because I haven't actually heard it described like this. But basically, so if you can imagine overfitting being a model that performs very, very well on the training data, but really doesn't perform well on the test data or in use, then the empirical risk is underestimating the expected risk. The chapter also put it in terms of your model being a hypothesis. And if you have an overly complex hypothesis that fits that training data very, very well, then it's not going to perform well because you have little data and the hypothesis is not very good. The model is complex, but there's not enough data to support that hypothesis. So possibly and likely means that you have too many parameters. And another way that they put it was that all modeling power during training is used to reduce that training error, as opposed to actually trying to generalize. Now, underfitting is the exact opposite. The model is not complex enough to adequately model the data, the underlying data. So the empirical risk and the expected risk are typically pretty bad. One of the ways that we prevent overfitting is regularization. And this basically prevents, what they call overly flexible predictors, which just makes the model better at generalizing. If we see this, where's my cursor? If we see this first equation, this is just, the sum of or least squares loss. Very, very simple. We have the input data multiplied by a set of parameters minus the actual values, and then we take the L2 norm or Euclidean distance between these two things and average that. We add then this regularization parameter, the L2 norm of this regularization parameter, with this lambda, which is a hyperparameter, which you can set and figure out what it is. Because this is much more simple, this term is much more simple than this is potentially, it basically forces the model to be more simple, more general. This is particularly with the L2 norm is called L2 regression, also known as ridge regression, also known as Tikhonov regression. I've never heard it called that before, but now you know. It should also be noted, I think an interesting point was, L1 regression, which basically just takes the absolute value of these parameters, makes this entire function not differentiable. So you can't actually use vanilla stochastic gradient descent if you're using L1 regression, because if you think about absolute value, it's not differentiable because you have a point at 0 instead of a continuous function. So I kind of found that fascinating. And there's some alternatives to training it, but you can't differentiate it. So before I go on, are there any questions or comments? Anything that?
Yeah, I have a question. I've always been confused every time I hear hyperparameter, because it sounds like the definition be changing on the time of day or something. At least in this context, because the way I understood a hyperparameter is like a set of parameters that you fix before training. Mm-hmm. Is that still correct? Or
yes.
Okay.
Yeah.
But does that meaning change in other contexts, or is it always that? And I'm just getting confused for no reason.
What do you mean by context?
Like, sometimes I hear the term hyperparameter thrown around in like other training models or something like that, or just another person talking about it, and like they'll describe it differently. I don't even know how to explain how different because it was confusing, you know. But I just want clarity. So hyperparameters are just predefined.
Yes.
Okay.
Now, if you're trying to pick the best model, you might do something like grid search or Bayesian search, where you search a set of potential hyperparameter values and you try and find the best model. But typically, they're not learned during the process. So you have a model that has, you know, parameters, or in a probabilistic model, you have like learned statistics. A hyperparameter is like something you said beforehand. You know, basically like learning rate, like I don't know, like temperature in some situations. But you know, it's outside of the training loop.
Okay.
So,
okay, cool.
Yeah.
Appreciate that.
Of course. Any other questions, clarifications?
Ted has one, I think, on the group chat.
I can't hear you, Ted.
No, I just had my hand raised. So I thought I would add a little bit of color. Let me start with the last question. So I don't know if you caught it. There was a comment in the book where they said, technically speaking, you can think of parameters and hyperparameters as they're all parameters. And so the most common usage is if you're doing gradient descent, if you're doing optimization, the ones that gradient descent, like you said, Liam, the one that gradient descent works on, we colloquially call those parameters. And the ones that you do search on, where it's set before you run gradient descent, you manually do it, maybe you do something like a grid search or whatever, we tend to call those hyperparameters. But if in your heart you really want to call them all parameters, you're not technically wrong. Okay. A few other comments just on the things that are on the slide. So, you know, you talked about the data points have to be IID. So like last week in the case study, Ryan had an example where we had 10-year-old data and we had data from the last year. Okay. There was a lot of discussion about, well, has the product or the customers changed in those 10 years? And if so, then the distribution of data for the 10-year-old data is not the same as the distribution for the most recent year. And that would violate the identically distributed part of it. And so hopefully that's like intuitive to people that like oftentimes when you run into data, it's not IID and you have to decide if you're going to potentially not use it or make some other type of adjustment for the fact that not all of your data is IID.
Absolutely, yeah. I'll give it another example. Stock market prediction. As you know, as accurate as that can be, oftentimes, you know, you will assume that individual data points are IID, but in practice they're not. So part of it is in the pre-processing part, you kind of need to, you know, do stuff like adjust your time window or do some fancy numerical stuff to try and force it into being IID, so it actually works with, you know, the lightweight family of algorithms that's required for like some high frequency purposes, you know. But yeah, like very good point. It's not actually IID in a lot of circumstances.
Yeah, that's great. And if you were predicting, you know, 8 tech stocks and you're predicting, you know, Apple and Google and Nvidia, they're not independent. There are things that, you know, one stock going up may cause the other to go down, or they cause them to both to go up or whatever. Or if you're predicting a stock based on like a whole bunch of financials, those financials are not independent either. So yes, oftentimes we stick with the assumption because we don't have anything better, but just it's helpful to know like possibly how thin the ice you're on is, so that you have a better understanding of whether you should have a lot of faith in the model or whether you should be, you know, skeptical of the predictions. I think another comment is where they talk about the true population expected risk, it's important to note that we'll never know that number. That's a theoretical concept that that we're comparing to, and since we never know that number, the definitions of overfitting and underfitting are unknowable definitions. So I still find them to be useful concepts, but just in practice, know that you need tools to decide if you're underfitting or overfitting, and you can't just go by that definition, because since you have no R true, you can never actually affect this, right? And the book talks about you use a test set as a proxy for R true.
Yeah, definitely.
Yeah. And sorry, Liam, one other final comment is, with the overfitting, oftentimes what we say is that we have data, and if the data were absolutely perfect and had no noise, then you could fit to it as tightly as you want. But if you assume that the data has noise, then if you fit to the data perfectly, then what you're doing is you're fitting to both the data and the noise. And we do think that the data will be predictive, will generalize, will be predictive in the future. But the noise we don't expect to be predictive of future samples. And so we have an example here, a very classic example like of L2 regularization. If you're familiar with deep neural networks, there's other kinds of regularization that we use, right? So you might be familiar with dropout. I do a lot of computer vision these days, and we do image augmentations. We add Gaussian noise to images. We add salt and pepper noise. We rotate them. We do different things. And I think the theory, the principle behind that is that we're creating noise that is consistently random. So for example, if you have 1,000 samples, the model may be able to fit to the exact noise of those 1,000 samples. But when we do dropout or when we do image augmentation, every time we do an epoch, we apply different random effects to those 1,000. So you're not able to then just memorize those 1,000 and predict to that, because every time you see it, you're getting different noise. So the idea is that if the noise is at a level of randomness that the model cannot predict it, then the model cannot overfit to that noise. And what it needs to do is it needs to fit to the data signal as best it can.
Definitely. And actually, there's a couple of points that they had in the book regarding probabilistic models and the noise, that asymptotic relationship. Ted, you might actually remember that as well. That's actually on a later slide. And I think that applies to non-probabilistic models, but actually, I'll double check when that comes up.
Yep. And sorry, one last final point. So anytime you do regularization, whether you're doing L2 or you're doing something like image augmentation dropout, that noise actually worsens your prediction in a sense. Okay. So you are no longer predicting the data, you're predicting something else. And so that's why, generally speaking, the rule of thumb would be you want to use regularization if you need to. You don't want to overfit, but you want to use the minimum possible amount of regularization, because you can imagine, I could just add so much noise that it's just completely drowning out the signal, and that guarantees you won't overfit, but it also guarantees you'll have a solution that's very far away from your true minimum,
Absolutely. And in fact, I that's a great segue into my next slide, actually. On that point, there was in the further reading part of this part of the chapter, they talked about Ivanov regularization. And again, I am really sorry for how that looks for the people here. But yeah, so Ivanov regularization, which I had never heard about before, is I did a little bit of digging into that. And that's a technique where if you have a regularization parameter, you can actually set a maximum value for it to ever be. And so if you have really noisy data, and you want to limit the amount of, generalization it does on that noise, you can actually set a parameter to, kind of clamp down on that and limit how much it, overgeneralizes. At least that's how I understand it. And then the other thing, which definitely wasn't in the book, but I'm going to talk about anyways, is really quick, is Morozov regression, which is actually you put a limit on the loss. And of course, I haven't used this particular thing before, but I kind of imagine that that might make the training process less sensitive to outliers. Like if you have maybe one sample that has like a huge error, or like a couple samples or something like that, like I can see instances where that would be useful. In the book, it actually links a particular article that was by a bunch of people whose names I forgot. And basically this paper here is where they prove that you can actually get the same results between Tikhonov regression or L2 regression, Ivanov regularization, and Morozov regularization. Did I say regression? I meant regularization, my bad. And interestingly enough, one more thing, actually, Ted, this is kind of specifically for you. I asked ChatGPT what Ivanov regularization is, and it gave me this, which is completely wrong. But I think it's kind of fascinating because it brought up the idea of adding a smoothing matrix to the regularization parameter. Like this can be like a Laplace smoothing function of some kind. And I mean, if we remember from linear algebra that this parameter is just like, a vector, and we have some, matrix L that we're using here, then I kind of wonder, apparently this is done in image processing a little bit. So I was kind of curious if anyone had seen something like this before. Ted,
There's a comment. There's a comment in the chat.
I can't actually see the chat.
Okay. And so it says the rationale behind the Ivanov regularization is to limit the energy of the network as represented by its weights, in one way preventing them to blow up. So that's one thing that we know is that, like, if you've seen the examples of polynomial regression, if you have 10 data points and you fit a 10th degree polynomial, you can get zero loss. You can guarantee it'll hit every single data point exactly. But it's likely to have relatively large coefficients and not generalize well. And so this is a general pattern where the simpler explanations, like a line that doesn't hit all the points exactly but gets close to them, will tend to have smaller coefficients. Whereas if you're trying to really jigger things in order to get it exactly right, you might need to do some crazy thing. Like, let's say the line almost exactly hits every point. So then just to like yank it, you might end up doing some bizarre thing like saying, minus 9,000 x to the 9th power plus 9,001 x to the 10th power, kind of a thing where it's just like, you're just doing this nudge, So what I would imagine is that this matrix L here that's applying the smoothing function, if you think of this norm as being like the total energy of the weights, then you can potentially apply some different weighting or whatever of the weights before you take the norm in order to alter how much you weigh things, so to speak. So that would be my guess, but I'm not familiar with either of these regularization techniques.
Well, fair enough. That's interesting. So I'm going to assume, Ted, if you're not familiar with putting a smoothing matrix in front of that, then it might not be that common. However, I did also find an example of Morozov regression, and it's right at the bottom there. And there was some data with like, a tau particle. Was that it? Okay, it was something where they actually used Morozov regression and or regularization to a good effect for some particular data. So I know I'm personally keeping these other alternate regularization techniques in my back pocket just in case. Any questions, comments, anything?
About the previous slide where we had this lambda parameter before the L2 norm of weight matrix, we actually I did some courses on machine learning, and in one of these courses we actually played with this parameter because if you make it very large, the loss function will regularize, will be able to minimize not the difference between predictions and the actual values, but the loss function will be trying to make down just these weights, like just to reduce the weights instead of making predictions correct. And if, of course, if we use, substitute this lambda parameter for 0 or very small number, then the effect of regularization will be just disappear. So it's like, I think, yeah, it's this common, so we can play with it and with this value, but we have to be cautious about very big values because like the model will try to minimize the weights itself, not the prediction, the difference between actual and physical values.
So you're saying like don't focus on the difference between the predictions and what we know, focus more on like how the weights behave?
Just on the actual values of the weights of the L2 norm of the weight matrix.
So a larger value for lambda has the potential to reduce the value or reduce the magnitude of the parameters, essentially.
Yes.
And I mean, that could be, very useful. So there's, later in the chapter, there's a couple of tricks that they use, that, people use to reduce those sorts of like, overflow or underflow. But I don't think, I wanted to create a working model for this, but unfortunately, had a busy week at work. So I wanted to have like a notebook to show this, but so just, it's there in the spirit.
Wait, quick clarification. Just make sure I understood what y'all were talking about. You're saying a larger lambda reduces or helps change the weight better? That's like
It just changed it up. It just tried to reduce the values, actual values of the weights, the absolute values of the weight matrix, instead of trying to find the optimal weights that there are actual difference between the actual values and predicted values. Instead of minimize this L2 norm, it will just minimize the L2 norm of the weight matrix, of the parameter matrix.
Okay.
There's like two large values because it will be like the second part of this equation will be more, like it will be much bigger than the first one, so the first one will be much less, so it will be no optimization process other than just making weights to like very, very low absolute.
Okay.
Yeah.
Okay, cool.
And exactly as you mentioned, like
It's just a scalar, right?
this can be a scalar or this can be a vector. Lambda. Oh yeah, that's a scalar.
So I mean, you make it bigger than beta squared.
Exactly.
It's more
Like
important to
yeah.
make it smaller.
Because if you think about it also, like this L2 norm is very simple, very general, it's very general sort of static function. So if you increase like the lambda, the equation relies more on that, general part of it as opposed to, the part that holds, I would probably say like the vast majority of the variance. So if you have a large value for lambda, this term becomes much more significant.
Okay. Thank you guys.
Okay, so moving on, they talk about cross-validation, and I assume the same for a lot of us. This is kind of something that we've heard of. But cross-validation, just that idea that the validation set is a subset of the data that evaluates the performance, and basically you divide your data into different folds, and all of the folds except for one you train on, and then you validate on the last one. And then they also put this in an equation, but the picture just makes more sense, to be honest. For each, it's this picture, honestly. Yeah, so that's pretty straightforward. However, there's actually some alternatives to this. So they go into nested cross-validation as well, further on in the chapter. But I think, in most cases, if you use K-fold cross-validation, I've heard of most people doing that and not complaining about it. But one of the alternatives that they give in the further reading was this idea of bootstrap and jackknife. And so bootstrapping, if for those who aren't familiar, I think bootstrapping is probably also should be covered when they talk about decision trees in the future. As they should. But bootstrapping is, taking random samples from your training data with replacement to try and get a subsample of that, data. In the same way you would take folds of the data and set aside some of it for validation, you would create a subsample using bootstrapping. And that can kind of lead to, creating data set with almost a normal-ish distribution from potentially non-normal data. And then you can estimate stuff like confidence intervals, precision, etc. Kind of as an alternative. On the other side of things, jackknife or jackknifing, which is something I've never used before, you specifically delete samples one by one. What they went into in the book, or they mentioned in the book, is this idea of bootstrap and jackknife, or rather jackknife after bootstrap. So this is the paper where they were doing some physics stuff with the tau lepton, or whatever it may be. And the solution was so they sampled using bootstrapping, right? But the statistics were different from the population or from the larger sample, and they could only figure that out after then applying the jackknife procedure to see how far off they were. I am not entirely positive when this would be appropriate as opposed to K-fold validation, but my theory is that in the last case study, we had an example where maybe we fitted on 50 samples and it did far better than fitting on 100 samples just because of luck, essentially. So I feel like K-fold cross-validation, if you have data with extremes, you could just get the subsample of data that is, lucky, or different. And doing bootstrap and jackknife, not only are you sampling with replacement randomly using bootstrapping, but you're also making sure that that subsample has the same statistics as the total training set using jackknifing. And so that's my guess. I don't suppose anyone is familiar with this at all.
I actually find it interesting that you mentioned that, the use cases, because I was curious about other people's instances as well. Because for me, I often work with non-normal data. So I have clients that are coming from very different backgrounds, ranging from client relationship management to telematics. I've done health in the past. And I've always found Bootstrap with replacement to be very handy because it was quite frequently when I was dealing with non-Gaussian, like non-parametric data. So it was kind of a really handy default for me to go to be able to randomly sample from the data sets, to be able to simulate different outcomes without making any assumptions about the distribution. So in practice, and this could be very different depending on their discipline, but in practice I found Bootstrap more handy or something that I turn to more frequently compared to k-fold validation. But I wouldn't say that like you have to pick one or the other. From my experience, you could also do both.
Nice. Yeah, I tend to actually like bootstrapping more as well. I mean, then again, I usually, like, if I'm implementing a particular paper, I usually just do whatever they say or try to. But yeah, like I do appreciate bootstrap. I also appreciate how you describe non-Gaussian data as non-parametric data. I like that description.
What's the difference in boosting?
So boosting is, so if you can imagine random forest, right, has like uses bootstrapping to create a series of weak learners. Boosting is like learning from the error to like fill in the gaps with weak learners that are trained on that particular error, more or less. I forget the actual, like, I don't have like the actual math handy in my head right now, but that's, generally speaking, the idea.
Yeah. The other thing is, it's that second bullet point there. It says calculate sample sizes. So from my previous experience as well, oftentimes I'm working with data where people don't know the sample size. So sometimes we'll start off with 30, right, just as a cutoff point because like there's literature that supports that 30 has an inflection point where you can start estimating whether or not it's going to reflect the population. But bootstrapping is really helpful when you don't know what that sample size should be.
Totally.
I have a comment regarding previous question. The difference between bootstrapping and boosting. Bootstrapping is what you do with the data. You actually take the data with replacement, and boosting is actual algorithm of how the boosting algorithms train their models, how do they create these decision trees. So just
Totally. Thank you both for that input there. I definitely appreciate it. Anything else anyone wants to add or questions about this particular process?
I think there are a couple of comments that are interesting on here.
Actually, if you have access to the chat, I would love for someone to, because I can't see them.
Yeah, sorry. This is Jean here, just reading other comments. It says, I read an article, there is a theoretical percentage you can access with bootstrapping is 63%. And another comment is there's a research article which shows that the best proportion for bootstrap is 62.3% with replacement, which is why it is used in random forest by default. So those two comments echo each other.
62.5%. And that's just completely static.
So I can add some.
Depends on the data because they probably use some let's say benchmark data sets. But we don't know what will be in our case because all the decision trees they heavily depend on the data, and all the time you add new data, you have to again retrain on the model.
Interesting. Yeah. So I guess that's like a generalization. Yeah.
Interesting. Well, I mean, honestly, if whoever it is wants to has access to that article.
Well, I think Ted is talking.
So Liam, I can add a little bit of color.
Why don't I have audio?
Can you hear me, Liam? I don't know if.
Okay, hold up. Oh no, it says Ted's muted on my screen.
Oh, I saw the little green box. My bad.
Yeah, no, I'm trying to talk, but I don't know if you guys can hear me. So, testing, 2, 3. I don't think you guys can hear me.
We can hear you in Zoom.
Yeah, I don't think the room can hear me for some reason. I think we just lost the room. I think they had a bad internet connection. While we're waiting for them to hopefully reconnect, what I was just going to share is that um, the the little bit that I've read about Bootstrap is that the technique is that you do um, sampling, random sampling with replacement back to the original population size. And this 62%, if I remember, is basically if you just do the math, the combinatorics. That's the percentage of unique samples that you're going to wind up with in your random sample with replacement. So you're going to have, 38%, 37 point something percent duplicates, and you're going to have 62% unique samples. And the really powerful thing about the bootstrap is that when you do bootstrapping, you tend to be able to uh, recreate any of the statistics of the original distribution. And again, they do not have to be Gaussian, so no assumptions about the distribution. So from the bootstrap, you can take the mean, and that will be a fairly accurate predictor of the true mean. You can find the standard deviation. You can actually do higher moments. You can do second, third moments. And so my understanding is that people have found the bootstrap to work very well if you're trying to do any of those things to understand properties of the original distribution.
I could add something because we use Bootstrap a lot in astronomy. And so it really works very well for representing the distribution of noisy data, even if the noise is very, very complicated. And so a very standard thing that we do if we have some signal, we bootstrap the data to try and figure out whether or not or how many sigma the signal is with respect to our noise.
Yeah.
Um, it's a very, very useful technique.
And if you do repeated bootstraps, it's not as prone to overfitting as if you just try to overanalyze your actual data, right? Is that accurate, Alex?
Yeah, absolutely. Absolutely. It really helps to regularize that.
Yeah, yeah. All right. I'm hoping the room's going to come back soon, but we shall see. So, there was a comment in the chat that Jackknife works pretty well for small samples. I don't know if it's just because since Jackknife goes one at a time, it's like uh, 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 expensive for large distributions. I just know that the conventional wisdom is that the Jackknife used to be quite popular, and right now, if you're just doing one procedure, as far as I can tell, the Bootstrap has completely become the uh, uh, the tool of choice, and that people don't use the Jackknife. Maybe Jackknife after Bootstrap is something, but Jackknife by itself, from what I've seen, has definitely grown out of favor.
That's very good to know. Just because they mention it in the chapter doesn't, and it was in the further reading as well. So that's my excuse for that. So I realized that my browser shut down. So let's try this again. Really quick, Ted, did you hear me talk about or start to talk about MLE?
No, we lost you from the Zoom, so we were still talking about the last slide. So if you don't mind, yeah.
Not at all. Not at all. Yeah. So, anyways, so where we have empirical risk minimization in non-probabilistic models, with probabilistic models, we use, something like maximum likelihood estimation. What they talk about is negative log likelihood, which is, what you want to, minimize in order to, find a model, a probabilistic model that is a good fit. So as you can kind of, see here, where is my cursor? We get the probability that, a particular value X occurs, in the data, given the parameters that we're, updating and training on. And then we add like the negative log to it. So the idea behind this is, those of us that were here for my last chapter, chapter 6, probabilities, might remember that if two probability distributions are independent or statistically independent of each other, then the joint probability of them is actually just the them multiplied together, right? Because that should make sense. Like if you were to like flip a coin twice, we can assume and hope that one of the coin flips is not going to depend on the other one. So if each of them is like takes as half and half, right? Bernoulli distribution with mean 0.5, then the result of two heads should be 0.25 because it just multiplied together. So if we assume that all of these, data points, these observations and labels are IID from each other, then the joint probability or the distribution of the whole data set should be the product of all of them. And so the reason that we add this negative log is because, and this actually took me a second, was that like, because these are all being, multiplied together, taking the log of it turns it into a negative sum, sum of all the logs. And then we use that as the loss. So what that does is it simplifies, our calculation considerably. And it also makes the result a lot more numerically stable. Because a lot of these, probabilities might be very, very small, and multiplying them all together might, is just numerically unstable and might lead to some, weird answers. So turning that into a sum stabilizes it. They also give this example of it as a Gaussian, or what if your probability is a Gaussian? Again, I'm sorry how this looks, but like what you would do in this particular situation is, if you can see really tiny there, you just substitute the exponential version or the exponential form of the Gaussian distribution in, and then they do all this math and they solve it and it becomes something like this. And if you can really see, you have, X, the parameters, Y, and then the standard deviation. So yeah, that's kind of how you would do something like that. Before I move on, are there any questions regarding log likelihood or likelihood estimation?
Liam?
You happen to know why we take the logarithm of probability?
Yeah. So, as I was saying, so you remember that like if I flip a coin twice, right, and I have to multiply those two probabilities together in order to get like, what's the probability that it turns up heads, right? Because they're independent. So we're assuming that all the data points are independent of each other. Like one data point isn't going to affect the other ones, right? So if we want to get the total probability of like a particular output or vector of outputs, given the probability of the data, because they're independent of each other, we would get that by multiplying them all together. Now, by the definition of a log, this is kind of similar to exponentiation. So if you take a log of that, you turn it from a product into a sum,
Okay.
right? And so if you can imagine you have a very small probability, like a 0.0001 probability of a particular, like, data point having a particular value, right? And you try and multiply them all together, you're gonna get a really, really, really small number. And that's gonna like underflow, or that's gonna be hard to keep track of, and that could completely break everything. So having this log format makes it so that, that doesn't happen. And then we make it negative purely because we can, because empirical risk minimization is a minimization function. So it mentions in the book that that's sort of just like an artifact, like a cultural artifact. It's the same thing,
I actually heard the demonstration why we are keeping this models is because after we apply logarithm, then our numbers become negative, and people just try to minimize the negative log loss, the function, then we will just go down, and we will not really minimize, we need it to be positive, so we can minimize it effectively, otherwise we will just go this function down.
Right. No, that makes a lot of sense.
Yeah. Log is always zero. It's always less than zero. So, because probability between 0 and 1.
Yeah, that's why we add this minus, absolutely.
Oh, okay. Actually, yeah, that makes a lot of sense. That's why it's a minimization. Okay. Yeah, that makes sense. Appreciate
Question I
that.
have is there any way empirically you can determine if your assumption of independence is incorrect?
Well, not with particular, like if your assumption of independence is incorrect. It depends. Honestly, it depends like what format the data is in. Like, if it's like time series, you can measure autocorrelation. You could measure correlation between different variables in particular ways. I don't know. I feel like there's a lot of different ways to figure that out.
Yeah.
Does anyone
you handle it in your processing of your training data before you even got to it?
Like, Personally, I would handle that in my EDA part of it. Just exploratory data analysis part of it, like just mess around with a couple of things, see if I can assume that it's IID. But actually, does anyone else have any like rules of thumb that they've come across for that?
What?
For testing whether your data set is IID. There's ways to also measure, like, say, like conditional probability of, say one feature against another, correlation and stuff like that. That's what I would say. Oh, and can y'all let me know if Ted's saying anything? Thank you. I appreciate that. Because
I wasn't, but just a quick comment. I'm also checking the time, so we probably have more materials covered. But it's important to understand that maximum likelihood is a point estimate. So if you did something like you tossed a coin 10 times and you got 5 heads and 5 tails, then if you had a very unfair coin, which was expected to be heads 90% of the time, then if you do the math, then the likelihood that you get 5 and 5 might be very low. It might be like, 0.1%. And if you had a coin that was 60-40, then maybe the likelihood of getting, that particular output 5 and 5 is whatever, 20%. And if you have a fair coin, then the likelihood of getting that maybe is, say, 23% or something like that. And so if you look at like the possibilities of, in this case, just one-dimensional, like, what the probability of a head is from 0 to, 99%, it's a nice simple function, right? And it has a peak at the top here. And so with half and half, it turns out that you're gonna, find that the type of coin that has the highest likelihood for a 5 and 5 would actually be a fair coin. Okay. But you can imagine in something that's much more complex. I was trying to think of an example. I can't think of a good one, but imagine you're doing like, I don't know, the electron orbitals around an atom or something like that. A point estimate is not a terribly useful thing there. And so transitioning to probably your next slide, Liam, this is why
Yes,
you want distribution.
Yes, but that's a very good point and something I forgot to mention. Yes, this is a point estimate. The probability of a particular value given a set of parameters. Further on, this is typically listed as like the likelihood function. If we remember Bayes' theorem, this usually gets put as the likelihood, but because it is the maximum likelihood, it is literally a likelihood. So, come on. Okay. Yes. So, in many circumstances, right, we want to actually estimate the posterior distribution, which is the reverse. Possibility of a given set of parameters given X, given data. And what we can do is we can add a prior on those parameters. So like I'll skip ahead really quick. Keep this equation in mind because I actually kind of had to wrap my head around this a little bit myself. The example that I kind of think of, right, and Ted, feel free to correct me if this is incorrect, but I have a background in like customer journey analytics and stuff like that. So imagine you wanted to set up an alert that sends out an email when an error happens like a given number of times. You don't know when like something is like anomalous or not, but you do have data pertaining to how many errors you've seen over time. So in this case, you could consider a Bernoulli distribution as the likelihood, the likelihood of an error happening at all. The prior distribution being a beta distribution, being like what that parameter is over time, and then what you could output there is say what is the percentile of this particular number happening in the last, like, say, 5-minute window. So if that percentile is like 95th percentile, then that might be an error. So that's kind of how I thought of it, is like, from that probability, you can infer, what it, like, statistical qualities about, the predictions, as opposed to just, a point estimate of like a particular value. But the way that they do that is by adding this prior. If this was, say, a Bernoulli distribution, the statistics or the parameters, which are statistics here, would be like mean. Yeah, it's just mean. And the probability distribution of that mean is the beta distribution because it changes over time, and depending on how many people, how many events you see. We typically don't know P of X. It's kind of difficult, but we can, say that is proportional to those two things. And that's where we can use stuff like conjugate priors. If you remember, the beta distribution is a conjugate prior of a Bernoulli distribution, which means that the posterior is going to be a beta distribution. This can be a Bernoulli, and this is a beta distribution. So this is like kind of the equivalent of like regularization, right? How I understand it. Like this decreases the amount that the probability distribution takes its error into account. And, given that previous example, you could maybe say that this prior narrows down the noise in that Bernoulli distribution, how it changes over the course of the day, into a prior distribution of, a beta distribution of what that means over time. So that's kind of how I have been thinking about it. Really quick before I move on to the next part of this slide, Does anyone else have like, any intuitions of this, which is, called map?
There was a comment in the chat, Liam, that kind of we would always prefer the map, but because it's mathematically intractable, we usually resort to the maximum likelihood.
Interesting. Okay, that's interesting. And there's also on like one of the later slides, there's like that integral being intractable. They listed a couple ways to get around that, or like algorithmic ways to get around that. I don't know if that's exactly the same thing, but yeah, okay. So as far as like maximum likelihood estimation goes, that converges on the true value. This is just a couple things that the authors listed. It converges on the true value plus or minus kind of like a normal error. If you had infinite data, it would eventually be, the correct, distribution, plus or minus this Gaussian error. And something that I know I'll be keeping in mind is that we usually expect the variance of that error to decay in 1 over n, where n is the number of samples. So if you have like 1,000 samples, you need a lot more. You need a lot more samples to decay that error, as opposed to if you had like, a small data set and something like that. So that's how that typically decays. And then if you have a small amount of data, that MLE can lead to overfitting. So yeah. So and why do we want to use probabilistic models? Typically because they have set rules that like a determinant or non-probabilistic model would kind of have to learn. Like we can say something like a Bernoulli distribution, governs the number of events that happen, and we don't have to like, guess from parameters, etc. So that seems to be the advantage of it. Yeah, like some of the ways that we use this prior calculation, or this map or MLE, it's being used in like topic modeling, click-through rate prediction, online ranking systems, and large-scale recommendation systems. I'm familiar with it from click-through rate prediction. So yeah, let me see. Okay, let me just check really quick. Okay, I'm gonna go fast through these because I think we've been lagging a little bit. Okay, so the idea behind when it comes to probabilistic models, there's also this idea of latent variables, which I think Ted, you alluded to really quick, which basically are variables that aren't learned but still affect the probability distribution. Like the example that I give is like, you could probably measure my heart rate and pupil dilation, and that might be related to my anxiety and might even be related with the more latent variable, which is procrastination, but you don't know how hard I've procrastinated, but you can see my heart rate and my pupil dilation. So it affects the generation of the data, but it's not, a learnable sort of parameter. But they gave a couple of different ways to estimate these things. The 2 steps that they used was to compute this likelihood without Z, and then use that likelihood for parameter estimation. So you can say like, give the likelihood of like a latent variable given, the data set and the parameters, or given, the data set, or, I'm not entirely sure what we would call this. Give the data set given specific latent variables. So, any questions, comments about that, latent variables? Because I know they're definitely used in like some more complex models as well. So, also.
Yeah, I'll say briefly that for me, the statistics gets hairy pretty fast. But the concept, I think, appears often enough that it's worth people spending a little bit of time understanding. So if you have, um, uh, I'll just say like a variational autoencoder, which is pretty well-known neural network architecture. To your point, Liam, the actual parameters that you are optimizing with gradient descent don't include any of those latency z, directly, but you are using it, and usually the reason why people want some kind of latency is because that z is going to be in a much lower dimensional space than your x. If z is higher dimensional, it doesn't really buy you much because it's computationally more expensive. But if z is a lower dimensional space, then that's helpful. And so you see that appearing in places. So, for example, we had these great diffusion models like DALI, and then Stable Diffusion used latent diffusion, where they actually, instead of doing it in pixel space, they were doing the diffusion in a much smaller dimensional z space. And so it was much faster, much less computationally expensive. And the idea is if it's a dog and you know what breed of dog it is and you know whether it's whatever, brown or black, like that's enough information in a much lower dimensional package to convey what it is that you're supposed to be doing. So it does appear, like you said, Liam, in a lot of different places.
Yeah, and I think isn't this one of the fundamental concepts in normalizing flows, or is that something else? I read like a normalizing flows paper once, and I can't.
I don't think normalizing. I don't know. Like I said, this is where the statistics gets pretty hairy for me. But I don't think it's a particularly important distinction in normalizing flows. Normalizing flows uses invertible functions. And so there may be some way you can express it via latence, or probably mathematically almost anything can be, but in terms of like what you do, yeah, you're just pretty much very directly parameterizing the functions that you want. And what's a pain in the neck is you actually want very expressive functions, but you want them to be invertible, and that's not easy. And so that's what took a while for people to invent some useful building blocks that are both expressive and invertible.
Gotcha. Okay. Well, if I come across a need for normalizing flows again in the future, I will keep that in mind. So, okay, so that's just like latent variables. I also hear the words latent variables used in papers a lot, so I think it's just like, keep maybe this equation in mind, honestly. But yeah, okay. So, oh, that's even like incredibly bad looking on the big screen. So they also gave this idea of like representing probability distributions as like a graph. So in this case, right, we have this like x1, or I'm sorry, x3, if you can see that, depends on x1. X3 depends on x2. You could say that like this arrow gives the probability of x3 given x1. And if you want to say, if you have like a series of like 5, values for all of these things, and you want to compute the joint probability distribution, then you use this algorithm, which is like, the product of each probability distribution of the node given all their parent nodes. So probability 2 given, where is that? Given x5, because x2 depends on x5. They gave a couple of different examples of different ways that this could be written, but honestly, like I feel like they were kind of
Uh-oh, I think we may have lost Liam again.
recorded.
Thank you. Let me try that again. Okay, hold up. And it came back. Okay, so sorry about that. I was just saying, yeah, I was just, talking about directed graphical models. I don't exactly know where that left off, but I basically was saying that I actually had trouble following like this idea of D separation. So this like that Y is B conditionally independent from D given A and C. And I don't really understand why. So if anyone read that and has a better intuition of that, feel free to chime in. Also, I'm going to move on.
So I struggle with this, okay? But let's just say you had a much simpler graph, which is A pointing to B pointing to C. So if you look at like the bottom of your slide, right? But get rid of the D and E. So it's just the three things in a straight line. Okay. So let's say A is how good of a student you are, and B is how much you studied last night, and C is your performance on the test. Okay? So C is not independent of how good of a student you are, A. Okay? Because if you're a good student, you're actually going to get better test scores. There is a relationship between A and C. However, given B, knowing how much you studied last night, it is possible for the C to then be independent of how good of a student you are. Because what's directly predictive of your test performance is how much you studied, not in general how good of a student and how much you always study. What's directly related is how much you studied for this test. And so that's sort of a simplistic example in which you can say, given A and C are not independent, but given B, you can now say that A given B is, or C given B is now conditionally independent from A. I do struggle with these things, but know that if you have a complex graph that represents a sort of real problem, if you can do this, then you can basically, again, when you have things that are independent, it means that you can calculate them separately and just multiply their probabilities together. So this is always a good thing. Anytime you can find things that you can calculate separately. Otherwise, you have to do this very expensive joint distribution. So that's my very oversimplified gist of the little bit I've been able to get my head around.
Right. Yeah. I feel like the way, in my opinion, the way that they like gave the D separated criteria in the book was a little bit hard to follow. Just my opinion, though.
It's correct. I just don't have intuition around it.
Yeah, but I think the cool idea is that you could potentially apply like some aspects of graph theory to probability distributions. And it did mention that there's a whole like programming language where variables are independent statistical variables. And I think it's called, what was it? Probabilistic programming. It was something like that. But like the idea that, you could even analyze like subgraphs of these, probability distributions, I just think is really fascinating. So yeah, if there's nothing else to be said about this for now, if anyone encounters a really, complex graph with probability distributions, might have to do a little bit more research, deeper dive, but I don't know. I just kind of like this idea at a high level. Okay, so I want to actually give kind of like an example of a probabilistic model, an HMM. And I'm doing this because I think, someone mentioned this in like one of the last meetings. And just to kind of like put this in perspective, is like, we did mention like latent variables. The idea behind a hidden Markov model is that there's a series of a series of latent states that we can't observe, that are distinct from what we actually do observe, and that we can move between these hidden states and get different observations, and there's a probability of you actually getting a particular observation if something's in a hidden state. So you can't see this up here, so I'm going to squint really hard and read it. But this graph here that I found online was, relating the number of ice creams eaten by Jason to these hidden states, which is the weather, So this is entirely probabilistic. And another thing to mention is that HMMs are based on the Markov assumption, which is basically like the future state only depends on the present state, not on, past states. So, which, so far we understand why that's a really good thing to at least kind of assume. But like it uses these transition properties, or probabilities, like what's the probability of moving from one state to another, and then what's the probability of observing a particular outputs, and chaining that together is part of it, and HMMs, I haven't used them in practice yet, but I kind of wish that I had in many circumstances. So I've heard about them, but that is to just give an example. Also naive Bayes, and there's a lot of other probabilistic models that you can use. So I also gave a practical example of this one if you're interested, and a more in-depth explanation. So yeah. So moving on, and this is very, very, very close to the end here, don't worry. So one of the other things, so we mentioned cross-validation. Now that we know more about Bayesian, properties, we now kind of look at this idea of nested cross-validation, which is basically just having an inner training loop as well as an outer training loop, where you validate the model within each fold, basically. And then the idea of Bayesian model selection, which is, kind of penalizing complex hypotheses or overfitting by placing prior on the models in the space of all the models that you can use. So in this case, they use this M to denote the actual model itself. And then you can say that the probability of having a particular model for a data set is equivalent to the prior on the models themselves by the likelihood of the data being produced by the model. So if I'm not mistaken, this is the framework if you use Bayesian parameter search for hyperparameter tuning. This is the basis for that, if I'm not mistaken, which is admittedly just a couple lines of code. So next to grid search and all the others. So does anyone have any questions or anything to add to either of these two things?
I just put a comment in the chat that if your model training is really cheap, like sometimes if you're doing a gradient boosting machine, then do 5-fold cross-validation, sure. If you're training a neural network and it takes 20 hours to train, then you probably don't want to spend 5 times that just to get the benefit of cross-validation. And so then nested cross-validation, if you do another 5-fold outside of that, means it would cost you 25 times as much. And so 25 times 20 hours, you just, as much as it's better, you're just not going to do it. So trust me, when they built GPT-4, they did not use nested cross validation, right?
Absolutely.
They could only afford to train it once.
Yeah, that's a very, very good point. Like whether these different techniques also depend on your resources. A couple of slides ago, like at the beginning when I mentioned cross-validation, they also said in that chapter that this is an embarrassingly parallelizable process, which you can split up over like multiple processes. But, again, yeah, if you're training a deep neural network, you don't really care about this quite as much. However, Bayesian model selection is more efficient than, say, grid search, which tries every single combination of the hyperparameters, because you can actually you can move with intention towards the set of hyperparameters that you want instead of just going and iterating through all of them. So
it's like, usually if you're doing a grid search, it's like assuming a uniform distribution of parameters.
yes, that would be a very good way to put it. Yeah. And then adding like a distribution of the models or the parameters, et cetera, prior that's different. I mean, they do that under the hood in like, what is it, like SciPy? I forget which one it is. They do that under the hood anyways. I haven't seen the code. I don't exactly know how they implement this, but yeah, they don't assume a uniform distribution. So yeah. Okay, so and just a little bit more to that point, you can do Bayesian model comparison, posterior odds, prior odds, and Bayes factor. So you can kind of use these metrics, I assume, to sort of you can use Bayes factor to, it favors the simpler model. You can basically use this to compare different, models to each other, essentially. How much for the prior here, like how much your prior beliefs favor, a particular model, and then how well, the model estimates the underlying distribution, et cetera. So, and then at the very end, I think these two are actually really, really important. The AIC and BIC. So you have like that log likelihood, right? So you can actually, the AIC, you subtract the number of model parameters. So you literally get, a metric that penalizes really complex models. The Bayesian information criterion, or BIC, you actually also, you penalize the model parameters less, but you also take into account the number of data points, right? Yeah, I think, and I mean, I've seen both of these used, but I don't think I ever had like a good understanding of what they did. So I would keep both of these in mind personally. So yeah, any questions or anything anyone wants to say about these two slides?
I think the last slide, the two criterion that you just said, they heavily used for feature selection. For example, for small data sets that are usually like biological and medical data sets, we sometimes want to find the features that are most predictive, and these two criteria that they are used for estimating. We either can train all the model on all of the features and then take feature one at a time and measure these two criteria to define if this particular feature is important for prediction or not, or vice versa. We can start with like 1 or 2 features at first and then add the features one by one and then measure the criterion, or just use these two methods simultaneously. So
I love that she said that, because that's exactly how I use it in my general practice as well. So to echo the sentiments of what she said in terms of like feature selection and using it as well for cases of like machine learning, ML explainability too. So you want to understand how your features are impacting your model, so that way maybe those decision makers can say, oh, okay, so these are the features and this is how important it is, right, for the outcome of my model. Then they can take that information to figure out how that model is doing. So that's really cool. I like the way you worded that.
Interesting. So when I do feature selection, which might actually be a little bit what you two are describing is probably more better. But I usually have used say a decision tree or something to give feature importances or something like that. How would you use these two criterion? These are the ones that you're talking about, right?
Oh, that's very easy. They call this, that's pretty good.
I would say that that's true too. And it kind of depends on the use cases as well, right? So it's like depending on the size of your data set, and when it really is important to use a small number of features to train your model, using AIC can be really helpful. So that way you can see, relatively speaking, compared to your other features, how much that single or particular feature is important for training your model.
Okay, so in this case, you would decrease the number of parameters, but you would keep the model parameters the same, essentially?
It really depends on the scenario. So in the cases that I used it for, we would decrease the number of parameters, especially the ones that aren't important for training the model, in cases where we have small amounts of data.
Interesting. Cool.
Hey, Liam, if I could add to that. So I've worked on a number of sort of simpler type problems, and so we were using linear regression or generalized linear models. And so if you're familiar with R squared and whatnot, basically, if you add extra features to your model, R squared always improves. It literally can never decrease. Okay. So it's hard to then say this is not like a maximization problem where you can find the sweet spot, because adding extra features always improves. So what you need is something which will give you a balance so that you can actually say you have a sweet spot. So there's adjusted R squared, and then really good ones are the AIC and BIC, because what you'll see is if you add extra features, if you add complexity, then based on the penalties built into these formulas, you would expect if they're truly contributing, then they're going to contribute sort of more than this sort of minimum noise information theoretic level. And so oftentimes you will see oh, I added this and my AIC BIC went up a little bit. That means that it is a slightly better model. You still could choose the slightly worse model because it's simpler, but you know that this is a slightly better model. If you just start throwing things in and the AIC and BIC go down, then what it really means is that you're probably just sort of predicting noise overfitting on these other features, and it's actually not helpful.
Cool. Well, anything else anyone wants to add? Cool. Well, that is my presentation then. Thanks everybody. Appreciate y'all, listening and contributing. So, yeah. Thanks everybody.